Hello there, I'm Andy Webster, and today I'll be talking to you about cross-validation. Over here on the screen you'll just see a bunch of words I just want to prime in your mind because they'll be relevant for thinking about cross-validation. But before we get to cross-validation per se, let's establish the motivation for building and deploying this kind of conceptual framework. Suppose that we have a prediction generator. This could be a linear model, a machine learning algorithm, or essentially anything that gets us from inputs to predictions. Now, we're interested in making good predictions, not just any predictions. We want our predictions to be accurate, precise, and we want them to be accurate and precise for other data sets, not the data that we have. So, other data sets. It's going to be very important that we avoid overfitting the model. Now, what we mean by overfitting the model is when we build a model that describes our data set extremely well, but it doesn't generalize to other data sets. And the reason that sort of thing could happen is that you may include terms in the model that you've built that only coincidentally describe the data that you have. They aren't doing real explanatory work. So we only want the inputs that are going to do real explanatory work. That way our predictions generalize to new data sets. Okay, but suppose we can't go get any more data. We've just got the data that we have. Well, we could split the data up. We could use a portion of the data to build the model. We'll call that the training set. And we could use a portion of the data to validate the model. We'll call that the validation set or the testing set. Well, the obvious way to do this would be to have any given data point be used either for training or testing, but not both. After all, we don't want our validation set to affect the training process, or else we're not really validating at all, are we? Then we're back to the kind of situation where we're just describing how far the model deviates from what it knows the truth to be. It's not really telling us anything about how well the model applies to novel data sets. This approach that I'm describing is not cross-validation, but what we would actually call holdout validation. We actually hold out a portion of the data set, and we just use that for validation. There are some benefits to this approach. It's fast, easy, cheap, and it does a pretty good job. There are some downsides. Cross-validation yields more efficient estimates. You get more out of each observation, so if you're on a limited budget, there's a good chance that cross-validation is going to be more appropriate, even though there are reasons one would prefer holdout validation. The model interpretation is more intuitive for holdout validation. Cross-validation, for reasons that we'll get into later, is going to lead us to a model built out of a bunch of other models, and as a result, the interpretation of the model isn't really going to be intuitive. So where cross-validation is very helpful if we only care about making good predictions, holdout validation can still be used if we want to make sure that our model is interpretable. So cross-validation is going to mitigate this trade-off that we face between using observations to build our model and using observations to validate our model. It's going to build on this idea of holdout validation, but it's going to leverage resampling to let us get more out of each data point. And I've also just listed a few kinds of cross-validation here, but we're going to talk about each of those in much more depth now. So the first major type of cross-validation is called leave P out cross-validation. The basic idea here is that we have n observations and we choose some value for P between 1 and n, really between 1 and n minus 1, because otherwise you'd be using 0 observations to make your model. We use P observations for validation and n minus P observations to build our model. And we're going to repeat that for every possible set of P observations. So that means that we're going to be doing a whole lot of cycles through this. In fact, we're going to do so many that this is computationally infeasible to implement for even pretty modest values of n and p. Except for one special case, which is also going to be a special case of the next type of cross-validation, k-fold cross-validation. So for k-fold cross-validation, we're not going to be using every possible subset as a validation set. We're just going to divide the data set up into k sets of equal size. We're going to use k minus 1 to build the model, and then we're going to use 1 to test, record the results of the test, and then repeat that, but using a different 1 subset as the validation set until you've used each of the subsets that we've made. So if you divide the data up into 5 subsets, then you're going to go through this cycle 5 times. But you'll notice that we're not going through every possible subset. We're just going through the subsets that we happen to make. So this is much more computationally feasible. People can actually do k-fold cross-validation. But it turns out that one particular kind of k-fold cross-validation is also leave p out, and that's called leave one out cross-validation. So leave one out cross-validation is both leave p out with p equals 1, and it's also k-fold with k equals n. It turns out leave one out cross-validation is a computationally feasible special case of leave p out cross-validation. It also happens to have the minimum bias of all k-fold methods, but it also has very high variance, and we care about both bias and variance, so from what I've read, most people tend to find k equals 5 or k equals 10 to be a better balance of bias and variance than leave one out. Although leave one out still has its uses, it's incredibly easy to do, and it's pretty good. There are a lot of great applications for cross-validation in agriculture, especially applied agriculture, because we're so often interested in making good predictions. A lot of the time we don't actually care about figuring out what's going on and understanding it. We just want to make better crops or produce more crops with the resources we have available. So one application is genomic selection. So this is a case where our marker effects are our explanatory variables, and then either a trait value or some kind of index that takes into account multiple trait values would be the dependent variable. That would be the thing that we're predicting. You could also have agronomic prediction models. Same idea, but plant spacing, tillage regime, which cultivars were in use, and the history of the site would be predicting yield or total profit or something to that effect. But you could use it anywhere where prediction is the goal and a massive designated test set isn't feasible for whatever reason. Sometimes cross-validation doesn't really do the trick. It kind of seems like cheating, and it sort of is, but it also works. It's not really cheating because it comes at a cost. It comes at the cost of being able to interpret our models, and it comes at the cost of a whole bunch of hassle and computation. But sometimes we want an independent test set instead of cross-validation. For an independent test set, we can make sure that the test set doesn't influence model prediction. Same thing for just holdout validation, but for an independent test set, we also can find new important variables that cross-validation isn't going to reveal. We can actually find out that there's some kind of pattern that the data didn't show, but which actually replicate. So hopefully now you're really excited about cross-validation, and now it's time for us to temper that excitement. There are some important limitations to cross-validation. There are very high variances in the estimates of fit based on cross-validation, and confidence intervals are actually really difficult to generate. So even if we could generate the confidence intervals, it would be difficult to compare models on the basis of cross-validation results. And it turns out generating those intervals is actually hard. We've also assumed that our validation set is representative of what we're actually going to be trying to predict? Are the random variables that we have a bunch of observations of in our validation set actually drawn from the same distributions as the observations that we're ultimately interested in making predictions about? You might be tempted to use this kind of approach for time series data, but don't. There are different approaches for verifying how generalizable time series analysis results are. Obviously, junk in, junk out. You probably hear this every time that you hear about modeling, but it's important to reiterate, if your data's garbage, you're not going to be able to make a good model anyway. This is actually an extremely important point because it's a mistake that people have made in high-profile genomics papers. You need to validate the entire procedure that you're doing. You can't do a filtration step where you narrow down a list of 1,000 predictors to the 100 best predictors and then only do cross-validation on the portion with the 100 best predictors. You actually have to do cross-validation starting all the way from that filtration step, which makes it so that cross-validation might not actually be as feasible for your work as it seemed. And if that does come up, then you might just need to accept the fact that you would be better off using holdout validation or designing an independent validation experiment. Thank you.